Hello and welcome to the Foundry by Forge College. So in our last explainer, we laid some serious groundwork, right? We looked at the specific roles of Bitcoin nodes, storing the chain, serving blocks, and maintaining the mempool. But knowing their job description is really only half the battle. How do they actually coordinate this massive, global, decentralized dance? Okay, let's dive into this. I want you to imagine a solitary node booting up for the very first time. It is completely alone in the dark. It has absolutely zero connections to the outside world, it doesn't know what the current blockchain state is, and it literally doesn't know who to talk to. The core problem we're solving today is exactly how that isolated node finds the rest of the network, learns the rules, and starts communicating securely and efficiently.
Think of today's explainer as an engineering schematic, a blueprint, really, for our decentralized gossip machine. We'll be covering joining the Bitcoin network, finding network peers, the art of gossip, a transactions journey, speeding up the network, and finally, preparing for consensus.
All right, part 1. Joining the Bitcoin network, the initial bootstrap.
Let's start right at the very beginning. That newly booted node wakes up completely alone in the dark with zero connections. So how exactly does it say hello world? Well, the bootstrap process is actually remarkably simple. It works a lot like checking an old school address book to find those crucial first contact nodes. When your node starts, it queries what are known as DNS seeds, or it relies on a few hard-coded IP addresses built right into the client software itself. You can think of these seeds like receptionists. They aren't going to process your transactions, but they will hand you an initial list of active, reliable peer addresses. And just like that, suddenly our node isn't alone anymore. It has a handful of valid IPs to reach out to and establish its very first connections.
Moving on to part 2, finding network peers and expanding those connections. Now, relying entirely on a few central seed nodes forever? Well, that isn't very decentralized, is it? Once that initial bootstrap is done, our node needs to start independently expanding its own social circle. It does this using two specific protocol messages, address and getaddr. It's basically a polite networking event. Your node turns to a peer it just met and says, "Hey, who else do you know?" using that getaddr message. The peer then replies with an address message containing a list of other nodes. Now, it's absolutely crucial to note that nodes are deliberately conservative about this address gossip. They validate timestamps, they check port ranges, and they actually prefer addresses from entirely different subnets. They're actively avoiding clustering so that the network stays decentralized, highly resilient, and essentially impossible to map out or take down. To manage all these new relationships, your node uses two types of connection slots, outbound and inbound, and this brilliantly illustrates the difference between them. Think of your node kind of like an extremely strict club bouncer. Outbound slots, which usually default to a target of 8, are connections your node proactively chooses to establish. It is entirely in control of who gets on the VIP list there. Inbound slots, on the other hand, are passive. It's the remaining capacity where your node just accepts connections from others. By controlling this topology, nodes can limit misbehaving peers by just flat-out banning them at the door, ensuring they are never overly reliant on one single source of truth.
So, just to quickly summarize our connection management tooling here. DNS seeds give us our initial bootstrap. Address gossip expands our routing table safely, and those inbound and outbound slots control our actual network topology. By the way, if you're fascinated by how different slot configurations change network resilience, Forge College has some really excellent wider educational programs where you can master advanced network topologies. But for now, just remember the main takeaway. A node carefully curates its friends.
All right, part 3, the art of gossip, inventory and whispers. So, now that our node has a healthy, diverse group of friends, how does the actual data move across this carefully constructed web? Well, welcome to the art of network gossip. To understand propagation, think of a juicy party rumor. Blind flooding is like walking into a crowded room and screaming a massive, complex secret at the top of your lungs to every single person at the exact same time. It's chaotic, it's redundant, and frankly, it breaks the internet by wasting a massive amount of bandwidth. Inventory gossip, on the other hand, is the far superior engineering choice. It's polite, it's highly targeted, and it saves our network from just grinding to a complete halt. The absolute core of this polite gossip is the inv, or inventory message. Before a node sends a huge block or a complex transaction to its friend, it just sends an inv message that contains a tiny identifier, a hash. It's essentially leaning over and whispering, "Hey, did you hear about X?" before actually telling the whole long story. And if the peer already knows the story, they say nothing, and we save all that precious bandwidth. It's pretty brilliant.
Part 4.
A transactions journey, from broadcast to network. Let's put this elegant gossip protocol into practice and actually track the life cycle of a single, brand new transaction as it goes from initial broadcast to network-wide awareness. This handshake works in 4 simple steps. Step 1, our origin node sends that short inv announcement we just talked about. Step 2, the peer checks its memory, realizes it hasn't heard this one yet, and replies with a getData message, literally asking for the full story. Step 3, the origin node sends the heavy payload, the actual TX or block message. And finally, step 4, the peer validates it and then turns right around and starts the cycle over with its own friends. So the crucial point is that we get this massive exponential spread across the network, but it is constantly tempered by targeted requests and strict validation checks. That's what keeps the network totally safe and efficient.
Now, this inventory gossip works great for small transactions, for sure. But let me ask you this. What happens when miners find a new block? I mean, blocks are massive. If thousands of nodes suddenly start requesting full megabyte-sized blocks from each other, all at the exact same time, we hit massive bandwidth friction. Latency goes through the roof. So how do we share these giant updates without crashing the whole gossip machine?
Which brings us to part 5, speeding up the network with some brilliant engineering upgrades.
To solve that big block problem, network engineers had to get really creative to keep our engine from overheating when the data payloads get large. Enter the compact block optimization, known as BIP 152, alongside headers-first synchronization. Here is the incredibly clever shortcut. Why send an entire block of transactions when the receiving node probably already has, say, 99% of those transactions just sitting right there in its own mempool? Instead of sending the whole heavy block, a node just sends the block header and a tiny list of differences, just the few transactions the peer is missing. This drastically cuts down the payload size, saving massive amounts of bandwidth and making block propagation almost lightning fast.
But wait a second, how does a node even know if its peer understands what a compact block is? Well, that's handled right when they first meet, during the initial version handshake, using something called service bits. You can think of service bits like little feature flags and node wears on its name tag. They declare things like, hey, I support compact blocks, or I support SegWit. Nodes use these bits to actively negotiate compatibility. If a peer happens to be running older software and doesn't have that specific flag, the node seamlessly falls back to the conservative, standard method of just sending the full block. That way, nobody gets left behind.
All of these tools essentially allow node operators to choose their own priorities on what we call the fan-out curve. Fan-out is simply how many peers a node actively forwards data to. High fan-out means you tell lots of friends instantly. You get incredibly fast network convergence, but you do waste a lot of bandwidth on redundant traffic. Low fan-out means you only tell a few friends. It's highly bandwidth efficient, but you risk slow convergence, which might actually cause late transactions or even orphan blocks. Ultimately, how you configure your node dictates exactly where you sit on this bandwidth versus latency curve.
Finally, part 6, preparing for consensus, synchronizing the truth.
Through deliberate connections, polite gossip, and those clever shortcuts we just covered, the entire global network of nodes is brought into a state of synchronized harmony. And that prepares the stage for the most important job of all, consensus. Let's quickly recap the mental models we built today. First, peer discovery mechanisms shape the physical topology of the network. Second, the inventory-based gossip model is a constant, ongoing trade-off between bandwidth efficiency and propagation speed. Third, versioning and service bits allow the network to undergo safe, progressive upgrades. And finally, the heartbeat of it all is that simple 4-step rhythm, inv to get data to the final payload. Let's move to and see how this builds our foundation for what comes next.
Because, getting the data quickly and efficiently, that is really only step 1. What actually happens when 2 nodes receive conflicting blocks at the exact same time? How do they agree on the absolute truth without some central authority telling them what to do? That is the real magic of validation and consensus integrity, which we are absolutely going to tackle next time. To continue your Web3 journey and dive even deeper into the mechanics we discussed today, visit forge.college to learn more. Thanks for joining me on this explainer, and I'll see you in the next one.